Hello, everyone, and welcome to Mechlin 360. So, in this video, I want to solve a problem with you to illustrate the concept of um, the normal stress as well as the bearing stress and the shearing stress. Okay, so let's read the problem together and then solve it. So, in this problem, we have two forces applied to bracket BCD. Okay, so BCD is a bracket, okay, which is pin jointed at C. Now, knowing that the control rod AB, so this is the control rod AB, is to be made of steel having an ultimate normal stress of 600 megapascal. So, ultimate normal stress of 600 megapascal determine the diameter of the rod, for which the factor of safety with respect to failure will be what? So factor of safety um, factor of safety will be 3.3. Okay. Now, so the first part says we should find the diameter, and then the second part says the pin at C, which is this one, the pin joint, is to be made of steel having an ultimate shearing stress. So we know ultimate normal stress. Now we are talking about ultimate shearing stress, which is what? 350 megapascal. Now we are also to determine the diameter at pin C, for which the factor of safety with respect to shear will also be 3.3. Okay. So again, the diameter at this joint. So if you look at it carefully, interestingly, this is the joint. And then you can see that these ones are here. So that is what we have here. If you look at it from the end view, when you look at it from the end view, this is when you face it. When you are looking at it in this way, but if you look at it from this view, you will see something like this. Okay. So we are to find the diameter. All right. So again, we should determine the required thickness. So that is the T of the bracket support at C, knowing that the allowable bearing stress is what? Okay, so part C, we should determine the thickness T of the bracket support at C, knowing that the allowable bearing stress B of the steel used is 300 megapascal. Okay, so this question is pretty much simple. We have to start from statics. So the first thing to do is to draw your free body diagram. Okay, so free body diagram is very important in mechanics, is to always draw your free body diagram. So for the free body diagram, it looks like it's already drawn. It's just going to be something like this, and then something like this. Okay, so this is the free body diagram. There is a load which is applied here at this point. So let's call it 15 kilonewtons. Um, there is a distance all the way to this point, which is what? 0.3 meters. Now, at this point, um, there is a 50 kilonewton force here. Then, at this joint C, that is also a distance. So that is a distance which is, um, 0.3 meters away. Now there is C, which is a joint. So we expect that for a pin joint, CX and then CY. Okay. So don't forget that there is also P here. So this is P, the load at the control rod. And then the distance from P to where C is 0.6. So this is the sort of free body diagram of the structure. So now the first thing to do here is our statics, which we can use to find the unknown reactions and the load. Okay, so without wasting much time, let's apply the laws of equilibrium of a rigid body. So for a rigid body to be in equilibrium, summation of forces along the S should be 0. So we have what? Minus P minus CX should be 0. And this is going to give us equation 1. Okay. And then what do we also have again? So we have summation of forces along the Y. Positive should be 0. So we have CY going up, minus 50 coming down, minus 15 coming down to be 0. After getting this, clearly we can say that CY must be what? So CY must be 50 plus 15. And what is 50 plus 15? Essentially, that is 65 kilonewtons. So CY is actually 65 kilonewtons, right? You don't need a calculator to know that 50 plus 15 is 65. Anyway, I've done it for you so that you'll be happy. So we have CY. So this was supposed to be equation 2. But then we need to find another equation which will come from moment. So summation of moment clockwise is positive to be 0. What do we have? For summation of moment, clockwise is 0. What are we going to get? We are going to take moment about C so that we can eliminate C. So from P, the moment about C is going to be counterclockwise. So minus 0.6 P, but then the 50 is going to be plus because it's going to be clockwise. 50 into 0.3 plus 15, because that one is also going to be clockwise, into 0.6, that is 0.3 plus 0.3 should be 0. Solving for P, what do we have? P is nothing but so this is negative, so we just go here to become positive. So 50 multiplied by 0.3, 15 multiplied by 0.6, then we just divide by what? 0.6. So what then is P? So P is going to be 50 into 0.3 plus 15 into 0.6 plus, divided by 0.6. All right. 40. So P is 40 kilonewton, Cy is 65, and then Cx. So to find Cx is going to be minus P from here. So then Cx is minus 40. But if Cx is minus 40, then it means that the direction we chose was actually wrong, but then the opposite. So Cx is supposed to come in the opposite way, and then we can see that Cx is 40 kilonewton, and the direction is to this way. Okay, but then the Cy we got positive. Okay, so that is it. All right, now at this juncture, I want us to look at this. Cx, P, Cy. So the magnitude of C is going to be the square root of Cx squared plus Cy squared. And what is that? So that is going to be the square root of 40 squared plus 65 squared. So the square root of 40 squared plus 65 squared, 76.32 kilonewton. So that is actually the load, or let's say the magnitude of the reaction at C. Now let's come back to the question. The question said at the A we should find what? Let's go back. He said that if the ultimate tensile stress is 600 megapascal, if the ultimate normal stress is what? 600 megapascal, that is for steel, we should find, for a safety factor of 3.3, we should find the diameter. First of all, let's try to understand the safety factor. You see, if you have a safety factor of 3.3, it measures how safe you are. Therefore, for a safety factor of 3, so your ultimate stress is supposed to be 600 megapascal. But then, if you allow a safety factor of 3.3, then it means your allowable is going to be 600 divided by 3.3. So in other words, your allowable stress is always your desired stress, or the design strength. Your allowable stress is your design stress divided by the factor of safety. Okay. So what is it? 600 divided by 3.3. And that gives us 181.82. 181.82 megapascal. So that is it. Okay. So since we now have the allowable stress, we can go forward and say that the stress is the load over the area. In other words, the area is the load over the stress. Now, what is the load we are talking about here? Don't forget that the load at P is going to act on the rod AB, which is the control rod. So what this means is that the normal stress here will affect that diameter, and that is the diameter you need to use in the calculation. And therefore, we need to find that diameter, which is going to be the load at P, which is 40 kilonewton, divided by the stress, and the stress there, which is the allowable, is 181.82. Therefore, what are we getting? So 40 times 10 to the power 3 divided by 181.82. Okay, so we have 219.99. So let's say 220 millimeter squared. Please take notice, 1 Newton per millimeter squared is actually 1 megapascal. Okay, so this is the area. To find the diameter is kind of very simple. So DAB, that's what we are looking for. It's going to be 220. Solving for DAB, we have 4 into 220 divided by pi. And then the square root, which is what? So DAB is 4 into 220 divided by pi. Oh no. Okay. And what do we get? We have 16.74 millimeters. In fact, this is the diameter of the control rod, actually. So that is the diameter. Now we are done with the first part of the question. Then let's come to the shear in the pin C. You see that the B part, he said that, look at this. He said that the pin at C is to be made of steel having ultimate shearing stress of 350. So we are to determine the diameter of the pin C. Again, this time the factor of safety with respect to shear is also what? 3.3. So again, we are going to use the same approach. Part B. The ultimate shear stress is 350 megapascals. Now we know now the factor of safety is what? 3.3. Okay. So if the factor of safety is 3.3, again we can go ahead and say that, you know, the allowable shear stress will be 350, which is our design shear stress, divided by the factor of safety. And so we have 350 on 3.3. And what is that? 106.0. So 06, let's just say 0.06. That's all. Megapascal. So that is the allowable stress, which we are going to use as our shear stress. And then, interestingly, we need to look at it carefully. Okay, let me do it this way. So we need to calculate. Okay. Now look at this pin. There is a pin, but look at it. If you look at the pin, there is one connection here, and there is also another connection over there. So there is this sort of double shearing here, because we have one here and we have one here at the joint. Okay, so since we have a double shear, to be able to calculate the diameter, we are going to use half. All right. In other words, think about it in the form of um you know okay, so you have one here, you have another here. So to compute for the diameter, what you have to do is to use half. Okay, so that if I have half and I have half, it will be what? 1. Okay, so the actual um okay, so allowable shear stress is going to be the load, which is the C divided by the area. But then I was saying that the C will be half here and then it will be half here. So to calculate it, we just need one of them, which is half C divided by the area. Okay, so then the area, so this one is also the same as C divided by 2A. So the area is going to be C divided by 2 multiplied by the allowable shear stress. So C, uh, so C is here, 76.32 kilonewton. So 76.32 kilonewton, all divided by 2 multiplied by the allowable. And that gives us the area. So we have 76.32 into 10 to the power 3 divided by 2 into 106.06. So the area we are getting here is 359.8, or let's say 7, oh yeah, 80 millimeter squared. All right, so that is the area we get. Again, using so pi dc squared over 4 is 359.8. Then dc will be square root 4 into 359.80 divided by pi. And what is it then? So dc will be 4 multiplied by 359.80 into pi. So 21.4, yeah, so 21.40 millimeters. So we know the diameter at C, and then we also know the diameter, the diameter at AB. Okay, now the last part of the problem before we go, the last part of the problem is saying that we should find so determine the required thickness of the bracket that supports, bracket support at C. So this is the thickness. So we have so this one, the thickness of this, that's what he's talking about. And how can I get the thickness? So I can use the bearing stress to find the thickness. The bearing stress is what? 300 megapascal. Okay, so now the bearing stress is given by the load divided by the thickness times the diameter. So if the bearing stress is what? 320, right? Uh yeah. No, 300. Okay. So the bearing stress is 300 should be equal to the load at C, which we calculated as what? 76.32 10 to the power 3 um divided by the thickness, which we are interested in. Then we multiply by the diameter, which is 21.4. Solving for the thickness, we have um so we have 76.32 10 to the power 3 divided by 300 into 21.40. Therefore, our thickness T is what? Um, so 300 multiplied by 21.4. Okay. And that is 11.89. Okay. Millimeters. So that is the thickness. All right. But then at the end of the day, um, oh, we were supposed to use half. You know, we were supposed to use half because there is one here and there's also another one here, just like we did for the other one. So half. Sorry, you're supposed to multiply here by half. Okay. If we do that, our thickness will be 5.78. Okay. So how was it 5.78? Just divide by 2. There you are. We are not getting this 5.78 because so the idea was that the collar diameter here will be used to design um you know a joint. So in practice, what you normally do is that you find the next whole number, because this diameter is actually a diameter which you are going to buy. When you actually go and buy a bearing, you will choose this diameter. So we don't have a bearing of decimal point. So that's why you have to choose 22. All right. Okay. But please put 22 here and then you realize that you will get 5.78, which is the actual thickness. But then for a design question, this one will be 22 millimeters. But if you are just solving it, then this is correct. Okay. So I hope the concept is clear. Thank you very much for watching.